Hi, I'm Mike Ault. I'm the Oracle Flash System Manager for Consulting for from Texas Memory Systems for IBM. I was brought over during the purchase of TMS by IBM. I worked with them for about 4 years, it'll be 5 years as of May, and I've been working with Oracle for about 20 years, since 1990, written several books, and presented at a lot of different conferences in and around the United States and of course internationally. So we're here today to talk about Flash and what it can do for your Oracle environment. We're here, of course, to talk about what can the Flash system do in your environment. Well, you probably all know these things, that your clients, your users expect high performance. They expect things to come back sub-second. It used to be 7 seconds was the golden rule of the web page, Now, if it's not flashing up there instantly, they're very disappointed. So that carries over to reports, it carries over to doing queries on the database. They want things now. It's the now generation, right? Reliability, they want 100% uptime, where in worldwide markets, that gives us about 2 hours of downtime when this crossing that one little part of the Pacific where nobody lives. So we can't have systems go down. A single system fault can't be fatal. As you saw from our architecture, we cover those cases. We try to make this as faultless as possible. And of course, also processing impacts your bottom time. You probably know more of that than I do. How much, if you have an hour out or 10 minutes out, how much time that translates into money. And of course, cost effectiveness. You want to make sure that this fairly expensive, low resource gets used effectively, and we can show you how it can do. And leverage checks can give you outsized performance gains. How about half a day's of work and your performance improves by a factor of 5? Would that be worthwhile? Yeah, how many of you paid for weeks of consulting to get a 10% gain? And reliability, of course, through all this can't be compromised, as you saw from our architecture. A single box standing there is very reliable. You mirror them, almost never going to go down, other than somebody spilling the Coca-Cola all over. Next slide. But where does databases and Oracle need speed? Okay, that's one question a lot of people answer all the time. Well, first, when you do queries, where does latency matter? Go ahead. So the user enters his query, it goes out and says, nope, it's not in memory, it has to go to disk. So now it comes back at the speed of whatever your storage latency is. Now, in most good cases, it's 3 to 5 milliseconds. Of course, if you're heavily cached, you may be down to 1 to 2 milliseconds. Okay? But still, you're in the millisecond range. Okay? So, reads is where you need, I don't care whether it's Oracle, whether it's DB2, whether it's SQL Server, MySQL. If you don't get your reads back fast, you're not getting performance. Okay, why don't writes matter? Well, in Oracle, they don't matter because they use what's called delayed block cleanout. Who remembers that term? Anyone remember that term? Well, essentially it means Oracle doesn't write a block out of memory until it absolutely has to. So it could be in there for seconds even, in some cases. Okay, and it writes when it can't find a clean block. It says, okay, memory, is there a clean block? Yes, then it doesn't do any writes. The visitor and goes through so many blocks and says, okay, I've scanned 5 blocks and I can't find any clean ones. Write some out so I can use them. Okay, and every 3 seconds it just goes up and cleans out some of the blocks, so there are clean blocks available. And when someone does a checkpoint or a commit, it does some writes there. But not all of them get out every time, just a certain batch. Okay. So where does writes matter? The user does an insert, okay, it goes immediately into memory. But then he does a commit, and it takes log writer, whatever your latency is, to write it out to the logs. Now, how many people are starting to see that creep up into their top 5 wait events? Log file sync. Log file sync showing up everywhere. Okay? And that's what's causing that. So where does it need latency? It needs, and the DB writer eventually writes that out at your disk speed. Now, is that important? Do you need to worry about that for performance? Not usually. Unless you're doing what? Like a batch insert or a batch write or a batch something. But during normal OLTP work or normal work at the database level, we don't see that latency because Oracle does it in the background. What we see is that that's what says that the transaction is done, is that log write. When that log write gets done, Oracle can rebuild that transaction. So it doesn't need to write that information out. Uh-oh. He's quick on the trigger over here. He's saying, hurry up, hurry up. Aren't I talking fast enough? Yeah, I'm living in Atlanta for 16 years, so it slows me down. Down there, remember, there's no such thing as a single syllable word in the South. Okay? Y'all, you know. I don't know. It's just interesting. But anyway. All right, so log writes, and again, eventually it got there. Go on. And now these ruined my stream here. Okay, where else? Okay, now in Oracle and in other databases, if you exceed the amount of space to do things like a sort or a hash join or a bitmap merge or any of these operations that require temporary space, if you exceed the amount that Oracle assigns you, where does it go? To disk. It's immediately a 7-time slowdown, at least. 17 times slowdown. Okay? Also, non-memory undo in Oracle. In Oracle, starting with 10G, they started doing what's called in-memory undo, which essentially, there's the undo logs and the redo logs. Redo is to redo the transactions, then the undo comes back and says, okay, that one didn't commit, get rid of it. That one didn't commit, get rid of it. Okay? So both of them are very important. But this non-memory undo activity has been slowed down or gotten rid of quite a bit in Oracle 10 and Grille. So we don't see too much of that. And if you're anyone here running Solaris, one, okay. How about Oracle Enterprise Linux? One there. A couple. Okay, so those are the ones that are concerned with flash cache. We may talk about it a little bit. We'll see. I can't remember if I took the slide out of this one or not. Next. Yep, I took it out. Sorry. But essentially, if your storage is high-speed flash cache doesn't buy you anything. We've done the test to show it that it's actually, in some cases, can be slower to have a flash cache when you're coming from our flash cache appliance, our flash appliance. So that slide. All right, so let's look at some benchmarks. Now, these are historical benchmarks. We kind of blue-washed them by calling them IBM flash storage, but they were on our RAM SAN appliances back before we were bought. So go ahead. This was the setup. We had disk array to do the baseline testing. About 90 drives. I believe it was a SAS setup. We had RAM SAN 500, which is the precursor to everything you've got now. It was the precursor to the 600 series, it was the precursor to the 700 series, and the 800 series. So it was our first flash array. Okay? And then I had 2 RAM SAN 400s, which were our DDR arrays. And what I put on there, I put system, temp, redo, the background stuff. Okay. So all the data indexes were either on the RAM SAN for 1 table space, set of table spaces, or on the hard drive. Use the same identical 4-node array to go against it. So I had a 4-node rack set up. This was the first version of 11.1. Go ahead. Okay, now the 500 had a latency of 250 microseconds. Still great, but not near what we've got now. Okay. Current IBM flash storage 25 to 110, 25 for writes, 110 for reads. Now, how many people does that kind of set off a little jingle in their head because they say, wait a minute, somebody told me flash was slow for writes? How many people have heard that? Anyone heard that? No. Okay. Well, we made it fast by putting in some DDR buffering, having a very aggressive write algorithm out of the buffer, and always writing to clean areas. And so we can get that very low latency. Also, we parallelize the heck out of it, as you saw from our architecture. Each one of those cards you saw in that picture, so 12 of them in one of them, has 2 controllers on it. And they're FPGA controllers, there's no software, it's all hardware, very fast. So we can do these writes in parallel and do it very quickly. The 400 and 440 were the same 16 microsecond latency, they were DDR based. But as you see, with 16 microseconds, that was really good then. We're talking 25 microseconds now with flash. So you can see why more and more the DDR has gotten phased out to favor the flash. Okay. So let's look at TPCC. How many is not familiar with the TPCC? It's an online transaction processing benchmark. Basically emulates a product delivery system. Okay. We of course tested both hard drives and the flash system. 9 basic tables, used 1,000 warehouse configuration, which is about 300 gigabytes. Not very big database, but a good test for this particular environment. Rep to 0 to 500 users. We actually had to stop at 300 users because the disk drives couldn't handle running higher. And we measured the transactions per second. All right, now this very busy graph what it basically breaks down to is these bottom 4 lines are the disk drives. Okay, so 1 node, 2 node, 3 node, 4 node. Okay, these top 4 are against the RAM stand. So 1 node, 2 node, 3 node, 4 node. What do you notice? 1 node on RAM stand beat 4 nodes going against hard drives. What would that mean in your environment? Well, let's say you keep 1 node for redundancy. So now you just got rid of 2 nodes worth of rack licensing. And you got higher performance. And this is with 250 microsecond latency. Imagine now with half that latency, what the responses would be. Okay, next. This was with reduced memory. How many of you increased memory? Increased memory. Oracle loves memory, right? Okay. So we went from a 1 gigabyte total combined SGA size across all 4 nodes, so about 250 megabytes each, up to about 9 gigabytes total across the 4. And as you can see, the disk drives quickly saturated at less than 200 users. And from that point on, we just couldn't get any performance out of it. While the RAM stand units still gave almost 10 times the performance and didn't saturate well beyond our 500 user limit. So again, if you're memory constrained, if you want to get rid of some licenses, if you don't want to spend that extra money, this makes sense. Next. And this is just to show what happened when we jumped up to the 630, which had similar latencies to what you can get with the 720 and 820. Still not quite as fast, but about double what the 500 had. And notice now this was a 1 node, 1 RAM stand test, and we got twice the number of transactions per second out of it. 7,000 transactions per second versus about 3,700 that we peaked out of the RAM stand 500. Again, showing that effective latency. Now, having the latency double the number of transactions per second, you can get out of the same type of system. Okay? So basically, in memory starvation, ramping up the nodes, ramping up the users, the flash system outperformed the hard drives. Now, could we have loaded hard drives on until we got similar performance? Maybe. But this was to test what would be a normal configuration. How many of you guys are running with 2,000 hard drives? Support 1 application. Not many, I bet. That's how many you probably would have had to load there to get that type of performance. Okay? But it just wasn't real. We chose 90 drives because that's usually probably more than most people throw at their situations. Even in a large parallelized unit with like an EMC or whatever, how many are going to be actually being used by one particular unit? Okay? So under anything we could throw at it, it outperformed it, especially in the OLTP environment where it's a lot of random read type activity. Next. Let's look at some modern results. This was Swing Bench. That's a benchmark that you can download. It's free. Against the V7000. So we're testing it against our midline unit. Okay, so the average response in milliseconds was 8, 28, 50, 82 for the 4 different types of processes that we were doing here. The DB file scanner sequential read, we did about 2.4 million of them, and it took 13, almost 14,000 seconds to do that. Okay? So our latency was 6 milliseconds, a little bit above, but then the test was really stressing out the system too. Okay? Go ahead. So what about on the flash system? This was an 820, 2, 2, 2, and 7 milliseconds for this process to complete. So that's a 2.5, 12 times, 6 times, and 10 times improvement. And this was just from switching, basically, the architecture we used was what we call our architecture. We'll talk about that in a moment. But switching from one set to another and saying, do the same test. That's all it took. And that was the fact of improvement we got in this environment. DB file sequential read, notice again, 2.457 million waits. But now they only took 808 seconds. And notice that the average millisecond wait was 0. Of course, that's because AWR's granularity is what? At 0.5 it says, 0.5 is 0 to it. Okay. So it's probably about 0.4, 0.3 around that area. So 10 times better on the flash system, and significant improvement was the DB file sequential read, which was at least 15 times better. Okay. So again, so just from putting this unit in, takes about a day. Bang, you're getting that much improvement in your environment. Next. Okay, TPCH. This is more of a data warehouse. This is a support type benchmark. There are two tests, power and throughput. Pardon me. Basically, power says how fast can you get all 22 done in a single thread. Throughput says now parallelize that based on how many warehouses or threads you set up, and see how fast it takes to run. Go ahead. 22 key queries. Same setup as the TPCC you saw before. We use a 300 gigabyte scale factor, which is about a 1 terabyte overall database size. Go ahead. Now what this graph shows is a ratio between the amount of time it took the hard drive to respond on the same query as the took for the RAM set to respond. So this is actually the factor of improvement we got from the RAM set. This is say. So you can see over here about 12. The minimum was just a fraction. There was a lot of CPU activity, it had a lot of I/O, and the peak was 25. Overall average is about a factor of 5 improvement in a TPCH environment. Okay, next. This was the throughput, where you got 8 parallel streams in this particular case. And as you can see, the disk drive performance just went off the rack. Okay. While the RAM SAN stayed fairly linear with what it was before. And what that shows is that the RAM SAN doesn't care. You're not repositioning things when someone else asks for something. It goes right to that address, gets what's there, and comes back. It doesn't have to move anything. It doesn't have to spin anything. It doesn't have to move an armature. It doesn't have to do any mechanical operations whatsoever. So it doesn't care how many people are going after it. Okay? So up to a factor of 25 for some queries. This would be an example of taking your batch window from 8 hours down to 19 minutes. Average improvement being a factor of 3.9 to 3.91 for the multi-stream environment. So about a factor of 4. An average factor of 5 for a single stream environment. So again, imagine if you could give a 4 or 5 factor of improvement in your environment from a single day's work. They'd probably say, great job, you're fired. But anyway, we don't need you anymore. Okay, swing bench results on the same type of test. Go ahead. This is the V7000. So the total execution time of 10, 9, 15, 6, and 11. The average response, as you can see, I'm not going to try and read those large numbers, but they're in the millions. Okay, for milliseconds. Next. So again, dropped again by a factor of 3 to 4, 3, 4, 8, 3, and 6. And the numbers also dropped 1.33, 2.9, 1.76, and 0.94. So again, not as much as what you'd expect because you're doing much larger reads, but still fairly good return on investment, I would say. And this was a comparison with the DS8800, 8870, which is one of our top ones, on our expected results. So to achieve 451,000 IOs per second required a 224 terabyte implementation on the 8870. That corresponds to, if you use 146 gigabyte drives, 1,534 drives. And if you do the math, that's what you get with the 200 or so IOs per second you get on a disk drive. Okay? And as you can see, we did it here with a 24 terabyte implementation because we don't have to spread it out across a bunch of disks. We've got actually more IOs per second, 463,000. Our gigabyte throughput was less, 5 versus 15. But that was 15 over there because you needed that for all those drives you were addressing. Okay. If you just stack 3 of our units over here, you've got that. Latency, 146 microseconds at the top of the range. Greater than 5. Lots, probably lots greater than 5. I'm not sure how much greater than 5. Okay, energy consumption, 500 watts versus 26 kW. That's a little bit of difference. Okay. Dollars per IOPS, 2.2 versus 10. So a factor of 5 higher there. Dollars per megabyte per second, 205 versus 131, but again, we could have played with that number and got it better. IOPS per gigabyte, 23 versus 2. What does this 2 tell you, though? You're going to be spending, how much would that cost? Anyone have an idea what that costs of that system, the 8870, with 224 terabytes? How much more from that? $2 million, I would say. Just off the top of my head. I don't know. I think around a couple $1 million. So, beating that 2 IOPS per gigabyte means you're getting a better price point. So when you reach that 2 IOPS per gigabyte, it makes sense to switch over to flash. Okay? And megabytes per second per gigabyte, 0.25, 0.21, about the same. But again, if you really looked at the cost here, to get there, there's 131 per SBC, 2 megabytes per second. I think those numbers are right for some reason. As I know, this unit over here would only run about, again, don't quote me on prices, about 350,000 maybe. So for some reason, I don't think that number is quite right. But anyway, you can see, much cheaper, less power, more power, as far as powerful system, as far as latency. How about the Storage Performance Council? How many people have heard of that? Okay, it's basically a agnostic benchmark just to test IOs per second and how efficient you are. So you can see here, this was a 630 test. I don't know if they have the 800s or 700s out there yet, but we're getting them. As you can see, out to 300,000 IOs per second, even up to 400 or 500, our latency beat everyone else's, and everyone else being mostly IBM. And what does that mean though in your environment? Switch to the next slide. Remember this formula? I won't go over it again. It's basically Lenz's law. Well, basically saying you can increase the queues and get performance. And as you can see from over here, 450 threads. What does threads do? That's queues. So this was a $3.6 million SBC system using 450 threads. How many CPUs to get 450 threads? Probably around 100 to 200. Okay. 297 million, 3 parts, 612 threads. So there's 300 CPUs. 2.62 million HPEVA, 198 threads. So it's probably at least 60, 70. Versus a $400,000 IBM flash storage system and 68 threads. 32 CPUs or so. So again, much better CPU utilization because you've eliminated all that weight that it does. Now, people are saying probably in their minds, if you know virtualization with IBM, but when it's not doing Oracle, it's doing something else. It's not just waiting there. But remember, Oracle does one little thing. Anyone ever heard of spin count? Can you file sequential read in Oracle? That's not sequential. That's random. I know it's confusing. Okay, there's 2 types of basic waits in Oracle when they're doing reads. There's a scattered read, and then there's the sequential read. If you file sequential read, it talks about the way it writes it into memory. It writes it sequentially into memory, you're just reading it randomly. Okay? The scattered read is more what you're thinking of, where it's reading one string of things, and then it's writing it in a scattered wise into memory. That's only random. Only random on it.
You guys mentioned that most of the flash units that are out there now are being slowed down because they're uncontrolled. You throw this behind an SBC, it's going to slow it down.
About 60 microseconds. About double per week. Alright. So, anyway, again, let's go on to the next slide and maybe get a little clearer. Okay, Opera has been used with SAP, with UCFS, with Oracle, with DB2, with SQL Server, and many more applications I'm sure we're not even aware of. Now let's see what we're actually talking about here. Is let's say you've got an application that runs 10,000 IOs per second. Now, if this is no LTP situation, you're probably talking 80% reads and 20% writes. Okay? So you have 8,000 per second reads, 2,000 per second writes. Excellent. Okay? So we take the IBM flash system as the primary copy, the preferred read copy, the preferred plex, the least queue, whatever is in your environment. And say that's the way it's going to run. Now you're doing 8,000 seconds now at extremely low latency. Does that mean your application is just going to take that and stop and wait for people? No, people are going to do more work. They'd probably be mad at you. But anyway, so next, what happens is storage was doing 10,000 IOs per second. Now it's doing 10,000 writes instead of 10,000 reads and writes. Probably doing them faster since it's not having to read this in the head all the time. The read-write ratio doesn't change, so what does that mean that the RAM stand's doing? Yep. So you do 10,000 writes into your disks, and now you're doing 10,000 writes plus 40,000 reads. What did you just do to your environment? You 5 times the previous storage performance from just adding this into the environment. Without changing your backups, without changing your application, without changing anything you're doing. And again, about a day's worth of work. All right, so the reads are serviced from the preferred mirror. In this case, it will be the flash storage flash system. Writes are synchronous to both the mirrors, so it's going to not going to acknowledge the write until it finishes at the disk side. Of course, what can you do? Now that you're not having to cache all those reads, what can you cache? You can cache all those writes. So you're giving them that cache speed. Okay? This eliminates what we call read poisoning. What is read poisoning? Okay, I'm going along on a disk drive, I'm writing, I'm happy as a clam, and now all of a sudden it says, oh, well, read over here in this sector. Oh, okay, over here. Okay, I'm writing along, I'm happy. Oh, read over here. Okay, so all that moving around to do all those reads poisons the drive, makes it go slow. So we're eliminating that. It can be used with any existing standard LVM as long as it has that preferred read capability. So it's nothing new we're adding. It's not a new technology. It's already there. We're just implementing it in a different way than what they envisioned. In initial testing, Oracle ASM was used, but we've also, again, with some tests, used SBC. So you can see the results. Yep. Who's heard of SLA? It's a silly little Oracle benchmark. Okay? So don't look at your neighbors. Anyway, okay. Basically written by one of the Oracle experts out there. It uses PL SQL. You tell the PL SQL routine what you want to do, and it does it inside the Oracle environment. So it's a pure Oracle benchmark. Workload consists of 56 users from both rack nodes. This is that 2-node system we just saw, generating DB file sequential reads. That's random physical, I guess you didn't catch that, random physical block reads. Test started with the preferred read set to the disk failure group, and then on the fly, in ASM, you use one command. While it's running, you can switch over to the other. So where that's important is if you've got a failure on the RAM stand, for example, you can automatically switch it back to the disk. You'd lose performance, but you wouldn't lose availability. Okay, next. So, can you see on the graph where it switched from I/O waits to CPU activity? Should be fairly clear. Right here. One command. Bang, all the I/O waits went away. Next. Here's some actual numbers. Went from 16 microsecond latency in that particular environment on the SBC down to what Oracle said was 0, which we know is just less than 0.5. It went from 60 megabytes per second up to 1,800 megabytes per second throughput. Instantaneously, one command. Went from 6,000 IOPS to 220,000 IOPS. No action on your part, no changing of indexes, no dropping this, no dropping that, no adding this. One command. Bang. Next slide. So essentially, number-wise, it went from 6,000 to 220,000. That's a 35, almost a 36 factor gain. 60 to 1,800 throughput, so almost a 29 factor gain in throughput. 16 microseconds, it's set down to 0, which is 100%, that's not right. We're down to about 24 milliseconds, microseconds actually here. This should have been a little U. Actually 24 milliseconds is right. 400 or so, which would be a 40 times improvement, not a 100 or one-time improvement. So again, basically a factor of 30 to 40 improvement in the environment with one chain. Now, does this mean that your application is going to run 30 to 40 times faster? No. Okay, I don't want you coming away from here saying, Mike said my application can run 30 to 40 times faster. It depends on how much your application is waiting on that I/O. If it's 30% of your wait time, you can get 30% of your performance back. If it's 90% of your wait time, you can get 90% of your performance back. It all depends on how much time your application is waiting for that I/O to complete. Next slide. So looking at some Oracle output, the DB file sequential reads, we're at 3,661,000. It took 56,000 seconds. Switched over, Now we did 142 million versus 3 million, and it took a little bit longer, 63,000 seconds. So basically a factor of 4 to 5 improvement there, just as we saw with the other numbers. The other telltale is here, the DD-CPU. Notice it went from 157 up to 4,700. Again, about a factor, in this case, I don't know, what was that, a factor of 12 improvement? 0.28 to 6.75%. That's nothing to snooze at. You know, I mean, you look at that, that's a factor, at least a 6 improvement in the amount of transactions being able to be processed. Okay? Okay, all this laboratory stuff is fine, but what about in a real-world environment? Let's look at some proof of concepts we've done recently. All right, this was Oracle e-business. Data gathering and reporting capabilities are to be tested. Processing the current volume of orders as well as scaling it to 10x and 30x the current volume. Next. The client production was a Power 795. We had to do it in our Poughkeepsie data center.